Right. So I think there was a question about course project. I'm going to go over like some of the details. I think that will clarify your doubts. And I think most of the doubts were clarified today in the office hours. Just give me a minute. Okay, I'm just opening a poll for you and you can respond to that and I will go over your questions. Okay, so I think question from Steve. Suggestions on reasonable projects using. Yeah, probably I think this will take some time. Steve, why don't you come to like one of the office hours to discuss this in detail? And probably if you can also write me an email with all these questions, because this is I think very specific to your project. Okay. Okay, question from Fernando. If we choose a course project tomorrow, will we be able to change it later in the case we find another more appealing? Fernando, yes, that will be fine, but keep in mind when you don't have a lot of time left, so you'll have to start working on the project as well. You don't just want to spend a few days working on it. Then, is there any question, Grace? Okay, so yeah, you can definitely make a switch. That's fine. But then again, when you make a switch, then we'll have to discuss that again in one of the session where we will define the scope, or it can be like through email as well. Okay, depending upon the number of students you have in your group.
Professor?
Yes, Mohit.
What is the submission deadline for the project, and are there any intermediate progress report presentations?
Yeah, this year there will be no presentation. It will be just your code submission and your report submission. And there will be one intermediate deadline, I think, in mid of November, just to make sure that you have started working on it and at least you have the idea what needs to be done. Because otherwise, like it will all pile up like towards the end, which is not good. And then students panic, and then we don't have time. We have to like a lot of other responsibilities at the end of semester. So we will have one interim deadline that won't be graded, but it's like mandatory to submit. And then the final deadline will be 9th or 10th of December, the end of the course.
Okay.
Okay. So Fernando, I hope your question was answered. Stephanie, is the final cumulative? I didn't get it. What do you mean by cumulative? So you mean like from the course point of view, like what will be covered? So final will be just after like whatever we are covering after the midterm, if that is a question. Are there any limitations on the project? No, Shane. There are no limitations, but again, it's a bit vague. Like, what do you mean by limitations? If you're talking about in terms of which platform you want to use, then definitely no, you can use whatever framework you want. And if you have like anything specific on mind, you can let me know. Okay. So question from Mert, are we going to have a final exam like the midterm? Yes, that's true, Mert. It will be exactly the same format. When are the final presentations? So Katrina, this year we are not going to have any presentations. So the only item remaining in this course from you is like the second programming assignment, and then the course project submission, which will include the report and the code, and then the final exam. Okay. Okay, question from Connor. If working alone, will the expectations be the same or more loose? Yeah, I mean, if you're working alone, then we won't expect like a lot of things in your project, right? So we will narrow the scope so that we are sure that you will be able to finish that, and that's what we are expecting. So we won't expect a lot. But if you have more people, then we will try to expand that a bit. So you are not at disadvantage if you are working alone. Okay, question from Austin. Is there a list of specific project ideas that we can pick from, or just choose something within the announcement list? Yeah, so the a list is there on the course webpage. If you are referring to that like as an announcement list, or because we never announced that, that was I think introduced like in the first lecture. I'm not sure if you have seen that. Austin, have you seen that list? Okay. Yeah, so then that's the list. But again, in that list can cover like multiple projects, just a single bullet point. So if you're not sure about what you want to do, let me know. I think some students came today in the office hours, so they were not sure. Then we assigned some projects to them. So that will be fine if you're not sure like what to do. We can choose it for you. Okay, question from Stanley. So we can choose anything for our project so long as it's related to the topics in the course. Yeah, that's true. Even if it's like a bit off topic, but it is using like the concepts which we learn in this course, that will also be fine. So we are a bit flexible in that front. So if you have doubts, like just let us know. Any bonus programming assignment? So Mosam, we are not sure yet because we haven't graded like all the programming, like all the students for the programming assignment. Once that is done, then we'll have a better picture whether we need it or not. We will make an announcement if there is a bonus programming assignment. Okay. Any more homeworks? I think there will be 3 more. 7 are done, so total there will be 10. So I don't remember whether 6 are done or 7 are done. So we'll finish like all 10 homeworks. We are working hard on a project and are planning to submit the paper to CVPR. It is okay to send the project to a conference, right? Yeah, I mean, you can submit the project to a conference. So Amir, I'm not sure what you meant. The first part was not clear. But yeah, of course, I mean, if your idea is great, you can definitely submit it to a project. The only restriction is whatever you are submitting as a project, you should not take credit for that submission in any other classes or any other like research items or somewhere. It should be exclusive, because then that will be an issue from the department, not from the course. Okay, I think this is the last question from Shane. When will the results from midterm be posted? Will it be curved? It will not be curved at this time. If we need to curve, we will curve maybe before the final grading. So this time you are going to get like the raw grades, and I think maybe just give us a couple of more days. We'll finish it up. Okay, so I think I have covered all the questions. If not, please let me know.
I have one question.
Yes, John, go ahead.
So can the project be as simple as if somebody has an implementation of like a VisSlam algorithm on GitHub, could we just like clone that repository and get it working on our local machine and then upload our own data set to it? Or do we have to make like the code, or can we just use somebody's repository?
Yeah, you can use someone's repository. That's perfectly fine. But put the citation that, put the reference that you're using the code from this GitHub. We don't expect you to implement everything, but then there should be some component in the project which is like, which you have done. Okay. As long as it is there, then it's perfectly fine.
Okay, got it. Thanks.
Okay, so two of the students find it very hard. And I think this is a nice curve. Let me share this with you. So you might see like this is a Gaussian, right? Maybe a Gaussian with a very, very small standard deviation. But yeah, I think it's a good curve, so that's fine. So yeah, let's go to the lecture, and I think this is going to be the easiest lecture in this course, and it's pretty short as well, so I'm sure we'll finish in time. And this is, so we were talking about features, and we covered a couple of strategies, couple of algorithms like HOG, and then we talked about a SIF feature vector. So those were kind of handcrafted features where we need some kind of domain expertise so that we can actually look into the images, into the data, and then design the algorithms. Like we want to extract edges, we want to extract histograms. So everything was like manual and handcrafted. So that was one way. On the contrary, we have a different way to extract features, which is kind of without having any domain knowledge, and this only requires data and labels, and the features will be automatically learned. Okay, so this is like we are moving more towards deep learning now, and autoencoder is something which can be used to extract features. And so let's first try to understand what autoencoder is. So the basic idea behind autoencoder is whatever input you have, you try to reconstruct or reproduce the same input. All right. And again, that input could be anything. It could be an image, it could be a video, it could be like maybe just a natural language, maybe a sentence in English. All right. So input could be anything. You will have to just reconstruct that input. So that is the main idea behind autoencoder. And while you do that, you actually try to learn some features. Okay. And this is, you can say that it's unsupervised learning because you don't need any labels. You just need that data. And as long as you have that, you know what you want to reconstruct. So in that way, it's unsupervised because we don't need any labels or annotations. But if you think about this, at the end, when you are reconstructing something, you do have to impose a loss function, a penalty there, right, to train your network. So don't, I mean, it's not unsupervised in that sense. We don't have to train it, because we do have to compute the loss function. And let's say we are doing autoencoding of an image. So we will reconstruct the image, and then we want to make sure that each pixel of the reconstructed image is as close to the original image as possible. So we'll impose a loss function on each pixel. All right. So this is a very efficient way to learn features. As I said, like we still need a loss function, even though it's unsupervised. So it's kind of implicit supervision to learn features. And in the contrary, like in supervised, we will need annotations or some kind of labels. So in this case, the input to the network is actually playing the role of label, because we are using that to compute the loss. Okay, so there are two main parts in autoencoder. You have encoder, and then you have decoder. Encoder is something which takes the input data, for example, the image, and try to generate a feature vector or some kind of encodings. And that's the first stuff. And then you have a decoder, which will take that encodings or the feature representation and try to decode it and reconstruct the original input. So these are the two components. And here I am just showing you a very basic structure of an autoencoder. So this first half, this is the encoder, and the second half is the decoder. X is your input. Again, it could be anything. It could be image. It could be as simple as a word. And then you try to encode it, which means you perform some kind of transformations. These could be fully connected layers. These could be convolution layers. And then you try to learn a code. So this Z code, this is called like the feature representation of this input sample. So it's a way of saying that, okay, you can represent your data in this compact format. And just the second part, which is called the decoder, what it does is it takes this representation as input, z as in, and try to reconstruct the original input x. So this is called x prime here. So this is a basic structure, but the actual implementation or the actual detail of this architecture could differ depending upon what your input is and what kind of architecture you are using to encode and decode. Okay, so if you try to compare this with like the classical algorithms we have in machine learning, then this is similar to PCA, which is principal component analysis, or SVD, which is a singular value decomposition. So we briefly covered SVD, I think, in the first lecture or in the second lecture, where we're trying to cover the basics of linear algebra. And the idea in both PCA and SVD is like you have a high dimensional feature vector and you try to compress that feature vector into a very, very small feature vector, which has like a very small set of values. All right, so you try to compress that data. And similarly, you're trying to achieve the same thing using autoencoder as well, because your encoder is actually taking the high dimensional data, which is image in this case, or any other high dimensional data, and you're trying to learn a very small latent representation of that data point. So in that terms, we have similarities. All right. So yeah, this is fine. Okay, so this just like comparison between these two. Now you can formally define your encoder as a function which takes data x as input and generates h. H is your latent representation, the z vector. All right. So this z vector, or this vector h over here, the dimensionality of this vector should be very small if you compare that with the original input, in this case this particular image. So if this image is, let's say, 28 cross 28, and this is a grayscale image, so it will roughly have 786 different values, right? So we don't want to learn a latent representation which has 700 different values, because otherwise we can just use the pixel values over here. So we want something very, very compressed. So it could be maybe 8 pixels or 16 pixels for this kind of input. I think that's sufficient. And then you have a decoder. Again, you can say that represent that in a form of a function. And the input to that function will be the latent representation, which is again the output of your encoder, fx. And the R is the reconstructed image. So what this decoder will try to do is take this representation and then try to generate what was fed as input to the encoder. So if you think about this, the idea here is we are trying to learn a very compressed encoding of the input image, and by imposing a decoder to reconstruct the same image, we want to make sure that all the information, all the critical information which is actually important for this particular image, they should be stored in this latent representation. Because if they are not stored here, we will never be able to generate this input sample again. Okay, so if we have all the required information, then it's possible to generate this. It's a different story that we will need a very complicated function or transformation to do that synthesis. But at least the first step is like we should have that information stored here. So that's the key. And if we can do that, which means that this representation is very powerful, which actually has all the information which is required to represent this kind of image. Okay, so it's kind of a two-step process, but the end goal is like something very, very interesting. I think there is a question from Daniel. It seems like this would have applications to super resolutions. Is that true? Yeah, that's true. So and again, we can have different variations of autoencoders. We can have a very shallow autoencoder, which means like you just have one layer like in the encoder, one layer in the decoder, and this is your hidden representation. And you can have very deeper autoencoders. You can have multiple layers, And again, this is your latent code. And again, you can have multiple layers and you can decode. And of course, not just 2 layers, you can have 100 of layers if your data is too complex. Okay, and as I said, like it doesn't have to be fully connected layer, and it can be anything. It can be a convolutional network. It can be even like a recurrent network, in which we haven't covered, I think, yet. Maybe later that will come. So it doesn't matter like what kind of architecture you use, but the basic idea will not change. So in this case, again, we have a convolution network here on the left, which is acting as an encoder. So taking the image as input and trying to generate a latent code. All right, and you can see here that the final layer is like a fully connected layer. So this fully connected layer is also part of this encoder. And again, so this encoding, which is like just 10 different values, this is being passed to a decoder. And again, it starts with the fully connected layer, and then you're just reshaping this, mean you're just reorganizing the values. And again, you are using deconv operation, but essentially you can also do convolution here. So don't worry about if you don't know what deconv is. You can essentially do a conv operation as well. And then you synthesize your original input. Okay, question from Dini. I think we covered that. Super resolution, I think we'll talk about that. So that's fine. Fernando, if you are learning the encoder and decoder at the same time, how do we know who's at fault when the output is bad? It seems like backprop would tend to blame the decoder the most since it's closer to the output layer. How do we mitigate that? Yeah, that's a very good question. I will say very insightful. But if you are training both at the same time, then ideally both are being updated, right? I don't think you should blame any of the networks. And I think what you're thinking is because this is closer to the output, the gradients are reaching this part of the network first, and the gradients are reaching this part of the network much after that. So that will happen, like let's say if you are having, maybe if you have diminishing gradients, right, your gradient is actually reducing as you move backward. So that's a problem which we face in deeper networks, but that's a separate issue. I mean, that has nothing to do with like encoder or decoder. So if you try to address that, and let's say you have batch norm, then again, it doesn't matter like whether your parameters are at the earlier stage of the network or later. I mean, they will still get updated. So if you were training this as a two-step process, you first train this and then you, but autoencoder, you can't do that. Actually, you will have to train end to end, right? So that's a good point, Fernando. But I think even if like it's hard to know, actually. So if you have a very specific problem, let's say you are going to use this representations later for some kind of classification task, we will see later how we can do that. Then you can figure out, okay, that classification is not working. Then you may know that, okay, then encoder is bad. But again, it's hard to control. Okay, so I hope I answered. I know I didn't fully answer your question, but again, it's complicated. Okay, all right. So let's see like a very simple example where what we are doing is we are trying to train at autoencoder for grayscale images. All right. So these grayscale images, they will just have one channel, and the resolution is 28 cross 28. So what we do is we try to compress them to just two numbers, which means that you have this encoder, and at the bottleneck at the center, you just have two values. And you use those two values to again reconstruct the same input image. Okay. Now, these are like some nice visualizations, and you will see that how effective your autoencoder is. So it's just learning two values for this whole image. And then the decoder can use those two values and reconstruct try to reconstruct the original image. And if you will carefully analyze like these images, it's preserving the shape pretty well, even if it's very complex. Okay. So the only thing which it's not able to preserve is like the fine level details. For example, if this is, I don't know, if there's a Nike shoe, so that symbol is missing, right? Because I mean, how much can you save like in just two numbers? And in this case, like the t-shirt, there is some kind of logo which is missing, because then the two numbers were not able to preserve this property. Similarly, like the linings here. But still, like, I mean, we can store like this complex structure in just two numbers, which is very interesting. All right. And if you look at the PCA reconstruction, PCA, like as I said, another algorithm where you compress your feature vectors. So it's doing a good job for some of the cases, but again, preserving the structure, it's not doing that well. All right. So this autoencoder performing much better than PCA in this particular case. Okay, question from Balganesh. Why do we use autoencoders? Is it used to reduce dimensionality of input? That's a good question. It could be, I mean, you don't use for reducing the dimensionality because, I mean, there could be some applications where you can use it, but for dimensionality reduction, I think PCA can do a much better job. So this is more of like learning features. Okay, so if you want like a very compressed representation of some sample or some input data point. So that's like a more inline application for autoencoders. And we'll talk about some of the other applications, I think later in the slides. CNN reduce input size and extract features, right? Please correct me if I'm wrong. Input size and extract features. Yeah, CNN will do that for you. And that's fine. We use CNNs for feature learning as well. And even in this case, when you have CNN, right? This is your CNN architecture. That's exactly what you're using. But I think the CNN you're talking about, probably you're saying like the classification networks. So the difference is for training a classification network, you do need labels, right? You need annotations. In this case, if you are paying attention, we don't need any labels. We just need data. Decoder is also a CNN. So you have a fully connected layer, and then you have convolution layers. And as I said, I mean, CNN, it could be fully connected as well. So autoencoder is a concept, like it's not an architecture. You can use like different architectures to implement an autoencoder. Okay, so I think that is clarified. Question from Momal. Does that makes autoencoder learn features usable for any CV task? I will not say that. It might work for some of the problems, but it's very hard to generalize because depending upon what the problem is, you might need different kind of features. Okay, so that's not entirely true. But for some applications, definitely it can be useful. Okay, so this was interesting, learning just two numbers. And as I said, you can use these autoencoders for feature learning. So what you do is you just take the input sample, encode it, decode it, reconstruct, and you can train this network like with any number of samples you have, like large scale samples without any annotations. Once that is done, what you do is you just get rid of like the decoder part, and then you just take the encoder, your train weights, and you can take your test sample and just extract this feature. So you can then use that as a feature extractor. And some good applications are, for example, probably I will have some applications. Okay, so you just take the trained encoder, get the features. So one good, very good application is image retrieval. Okay, so image retrieval is, you might have seen this like in maybe Bing image search or Google image search. So the problem is, instead of like your textual query, you send an image as a query. For example, this particular image, so two horses are running. And then what you want is you want similar images as a result. All right. So for example, if you send in this as a query, what you will want is images like this, which looks very similar. and your database will be like very huge, maybe million or billion or trillion of images, and you will have all the variety of maybe horses. There will be like other objects as well. So this is called image retrieval, where you have a query, you have a huge database, and you match that query with all the images in the database, and then you select like what are the best matches, and you present those to like the person who is querying the image. So these are the results. So that's the very standard problem in computer vision. It's called image retrieval. Now, how autoencoders can help you is you can just train this kind of autoencoder in on a lot of images, and once trained, you can take this encoder, and what you will do is you will use that the encoder part on all the images in your database, and you will get like that small embedding for all the images, and then you can also get the embedding for the query image. And then what you have to do is you just have to match that smaller feature vector. So you will just perform one-to-one matching, and then based on whichever vectors are like the closest, you will just select some top such feature vectors, and then you will show the corresponding images in the database as a result. So you don't perform pixel-wise matching, you just match that feature vector. So that's a very, very good application. Okay, question from Shanyang. If we mask some of the pixels and predict them, is it still considered an autoencoder? Yeah, that's still an autoencoder. That's right, Shanyang. In fact, that idea has been used like in a lot of applications and many different problems. That's a very interesting idea. So question from Brandon. So an autoencoder is feature extraction from the encoder, and decoder is the matching. No, decoder is not the matching. You don't use decoder, you just use the encoder. Matching, you can just compute L1 norm between the feature vectors of two images. Okay. Another interesting application is denoising. And what here you can do is you can take like your clean image, and you can manually like put some noise, like let's say salt and pepper noise, Gaussian noise, or any arbitrary noise. Now you have the clean image, you have the noisy image. What you do is you use your noisy image as an input to encoder, learn the compressed representation, and then using the compressed representation ask the decoder to actually construct the clean image. And you can do that, you can compute a loss because you already have a clean image, which you use to generate this noisy image. So then what's happening here is this autoencoder is trying to filter noise from this noisy image. So it's trying to learn a compressed representation by avoiding noise, and then decoder is just using that representation to do the reconstruction. Now what will happen is once you have such a trained network, you can take like any noisy image like in the from the real world which you have captured through your camera, and you pass that to this autoencoder, and it will automatically clean it. So essentially you don't need any labels like to train this. Okay, so that's pretty interesting. Question from Ruchia. The autoencoder will store the information of the images in pixels. Store the information of the images in pixels. Ruchia, I didn't get your question. So autoencoder will try to learn a latent representation, which will be like few numbers. For example, in the earlier example we saw, it was just learning 2 numbers. But in real world, it won't be 2 numbers because those were like simple images. So you try to learn a very small feature vector, which could be like 32 bits or 64 or maybe 128, something like that. Was that your question? Okay, you can confirm. I can go through other questions. This is very similar to single pixel cameras. Yeah, that's a good point, Adam. So question from Fernando. Is there a good rule of thumb to know how much compression the encoder should do? Yeah, that's a very good question, Fernando. It depends upon like the complexity of your image. For example, if you're trying to compress a video, I mean, 10 might not work, and you might need a longer feature vector. And for images, it would not be that long. And again, if it's a grayscale image, it might be again very short. So 28 cross 28, if you're learning 10 values, again, that's not enough like for even for your digit classification if you have a grayscale image of a digit. So again, that comes with like experimentation. There is no rule of thumb, but ideally you learn feature vectors. Let's say for 28 cross 28, maybe you can learn 16 bits. Okay, and maybe for 224 to 224, you can try learning 32 or 64. Okay, question from Momal. Does Autoencoder have any application in NLP domain? You can do all the things like which we are doing here in a sentence maybe. So one good application, I think, could be sentence completion, right? So you can actually take a long sentence and maybe just remove some of the words in the input, and then ask the autoencoder to generate the full sentence because you do have the ground truth. And then you can use that autoencoder to solve the problem of sentence completion or fill in the blanks. Yeah, but that's a very good example. Okay, Ruchia, in what format will the decoder receive the input in case of image? The decoder will receive the latent representation, which is like a compressed feature vector. Okay, if it's two numbers, it will just receive two numbers. If it's like 32 dimensional long, it will receive 32 numbers. Is it clear, Ruchia? Okay, good. Okay, question from Brandon. Could an autoencoder be applied to do crowd counting? Crowd counting, how will you do that? Because for crowd counting, you need to predict the number of people present, right? And you need annotations for that. So I'm not sure like if that can be done using an autoencoder, but yeah, you can think of some solution and that will be a big thing. So that's denoising, and I have a couple of other applications. Let me quickly go through those. You can use it for image colorization. And essentially what you can do is you can have a lot of colored images. You can easily convert them to grayscale. That's pretty easy. And you can train an autoencoder using where you send those grayscale images as input. And since you have the colored image as well, which you actually use to create the grayscale images, you can ask your decoder to synthesize this colored image. And then you can easily train it because you have the ground truth, you can compute the loss. And once that network is trained, you can send in like any grayscale images, your old photographs from a childhood, and then your network will be able to give you the colored images. Okay, so that's interesting. And this is again a very, very interesting, I think, idea of anomaly detection. So the idea here is you train your autoencoder on normal images, right? So you can have a lot of normal images where you know for sure there is no abnormality at all. Now, once the network is trained, then that network knows that, okay, if you have such kind of input, then it will do the reconstruction. Now, what will happen if we provide an image where we have some kind of abnormality, which the network has never seen? For example, let's consider this case where there's a walkway and there are trees and there are people walking, right? So the network has always seen people walking in the street. The network never saw like any vehicle walking or which are being driven in this road, right? So if we pass an image in which we have like this kind of vehicle which was never seen by the image, then what will happen is the network will not be able to do a proper reconstruction of this vehicle. And that way we can easily compute that, okay, which portion of the image was not reconstructed well. And if you find like an outlier there, we will know that this is an abnormal image. So that's a pretty cool idea to do anomaly detection. So some properties of autoencoder before we end today. So first of all, like it's very data specific because your networks, your trained autoencoders will perform well when they are tested on like data points from the same distribution. So it's very data specific. And the other issue is like your reconstruction will not be that great. It will be like some kind of degraded reconstruction, so it's kind of lossy. You lose some information. And earlier I showed you one example, right, where you just try to learn two numbers, so then you were losing some of the fine details. So if you have very complicated data, then it might not be uh, possible to learn all the complex details from your input samples. Okay, so the good thing is it learns automatically from examples, so therefore it's very easy to train. And if your data samples are like similar to your training samples, it will perform pretty well. All right, so I think that's all I had for autoencoders. I think there's one more question from Balganesh. Does encoder has significant application on segmentation task? So when you say encoder, you mean like encoder from autoencoder, right? Segmentation. Yes, go ahead.
Yes, professor. Like they said, I have read the article on semantic segmentation. So in that they mentioned like they use like even encoder is a part of the whole network. So by the time I haven't known much about encoder, so I just asked.
Yeah, so encoder, I mean, this is just a term, right? But if you look at the architecture, it's similar to your classifier. You use similar architecture for a classifier as well.
Okay, got it.
Right. And segmentation, if you have a good knowledge, then you might know that it uses like a unit kind of architecture, right? Where you first have an encoder and then you have a decoder.
Okay.
And again, encoder tries to compress the features similar to like we saw in autoencoders.
Okay.
And then decoder tries to do the segmentation. So that decoder is similar to the decoder we saw in autoencoder. The only difference is the type of output it's generating. The structure could be almost similar.
Okay, okay, that makes sense. Thank you.
Okay, so question from Momal, can you explain the anomaly detection? Okay, so let me go back. So in this one, what we do is we use images where there are no abnormalities, the normal images. For example, let's say presence of a vehicle is an abnormality, right? So we train the network where we don't have any vehicles. Then the network will know like how to extract features from these visual patterns, right? There will be people, there might be a group of people, or trees or streets. There might be like lighting condition, changes in lighting condition, different variations. All those are fine. But so that's how we train the network. Now, during testing, what we will do is we take that trained network and we send in an image where we have an outlier, for example, a vehicle. Because the filters or whatever operation you are doing in your network, those filters have never seen such a pattern. So then what will happen is the network will perform like abnormally, right? It will not perform as expected. So when that will happen, the reconstructed image which the decoder will give you will see like some kind of abnormalities at this point. So it will still be able to like reconstruct all these people here, the trees, but this region it will not be able to reconstruct because it has never seen such a pattern or such a texture. And then what we can do is, yes, go ahead.
Yeah, so if we want to automate this thing, Professor, like if we want to build an anomaly detection pipeline, then if we give an image which have an anomaly to this trained network, the loss of the network would be high for that particular image at the time of regeneration. And that's how we'll be able to tell that this particular input image had an anomaly.
Yes, that's correct. That's correct. And you can actually you can also locate like where the loss is high. So you can also locate that region. Where is the anomaly? Okay.
Right. Thank you.
Okay, question from Daniel. What did the motivation for autoencoders come from? Seems like it draws inspiration from something like cryptography. So I'm not sure whether it came from cryptography or not. Yeah, I'm not so sure like what's the exact source. So I will have to check that, and probably I can include that in the course for next year. That's a good question, Daniel. I'm not sure about that. I will try to find it out today and let you know later. Okay. Okay, question from Mohammed. GANs transformers are different architectures inspired from autoencoders. GANs transformer, those two are like very different concepts. So GAN is something different, transformer is something different. And yeah, more. I don't think we can correlate GANs transformers with autoencoders. They are totally
But both
different
of
concepts.
them have a encoder and decoder, Professor, no?
Transformers, but that's different. Yeah, they do have encoder decoder, but let's not confuse those with the autoencoder we are learning here. I mean, there is some correlation, but again, that's a different concept.
Okay.
Okay. The high level idea seems okay. I mean, if you just look at the encoder, it might give you the encodings of input data, and decoder might be giving back the data. So the high level concept is same, but transformers are like much more than that. The actual working
Of
of
course, the
transformers.
architecture have activation and everything. So
Right. Okay. So if you think about like how they came up, I mean, it's not, I mean, although they're calling it autoencoder, if you think about it, it's not reconstructing the same input, right? It's trying to do translation. So if you look at the original work, there they try to convert like sentence from one language to sentence from another language. So it's doing the translation. It's not autoencoding. Okay,
yes,
but yeah,
that's
the
true.
high level concept is similar, and you can say that okay, the architecture is more complicated with some more some other insights, some other intuitions. Okay.
Right, Professor. Thank you.
Question from Fernando. Any course projects that you would recommend for groups of one? So Fernando, can you make it to like office hours, maybe on Thursday, or write me an email after the course, after the class? Okay, great. So the course project, let me, okay. So the course project, if you have not decided, if you have decided, that's good. And we are flexible. I mean, it's not that if you have, as I said earlier, if you have picked some project and you want to change later, perfectly fine. But we want you to discuss with us like what you are choosing and what should we expect from the project so that you can complete that in time. So the only concern we have, as we have seen before, we don't want you to take like very bold project which you can't complete. That's not good. So that's why we want to know what exactly you are doing so that we can limit the scope if it's going to be impossible to finish that in a month's time. And so that's one concern. The second concern is if there are multiple students in the same group, we want to make sure that every student is actually participating, every student is contributing. Okay, so those two are the main concerns, and as long as those two are satisfied, I think all is good. The third point is regarding use of external code. That is perfectly fine, you can do that for course project, but whenever you're doing that, you need a citation. Refer to that website or GitHub link, say that okay, we have used this piece of code from this website. So it should be pretty clear that which part you have done and which part was already existing. So that will help us in grading. Okay, and of course, like if there are more questions, do let me know. We'll be happy to answer. All right, so let's end it here. Thank you.